In this lecture, we will discuss properties of covering maps. So let's begin with a definition of what a covering map is. Definition: we say a map pi between two topological spaces x and y is a covering map. Of course, it's assumed it's continuous, and we will not bother even writing that down. When pi is surjective, which should make sense because otherwise why would we call that a covering? And for each p in y, we can find an evenly covered neighborhood. So that means we can find something that's an open set in y. We want u to contain the point. Also, let's add u is path connected. And, well, maybe we could make this assumption. So let's make this assumption. So this is an assumption. This is not actually required in the definition, and depending on what kind of book you're using, some people might assume these things, some people might not assume these things, but let's just make the assumption that all spaces are path connected and locally path connected. And in fact, we can even assume, maybe at some point we'll even assume that we have things that are Hausdorff. All of these are very reasonable assumptions in the way this kind of math is used in other places. Now, you can, of course, define things in a more general kind of a way without these assumptions, but it's just that in practice, when you're using the theory of covering spaces, the kind of spaces that you deal with will satisfy these conditions anyway. So let's just assume it without making it more complicated for ourselves. Now, if we're assuming things that are locally path connected, we can add the assumption that this neighborhood is path connected. If you look at certain books in topology, when they define a covering map, they do not necessarily assume that U is a path connected set, but because we have this locally path connected assumption, it means that given an open set that contains a point, you can always find something smaller that contains the point and happens to be path connected. So because of this extra assumption, you're permitted to get away with just assuming this. So U is path connected, and when you pull it back and pi inverse, and if we write, so if you pull back U, you will of course get an open set in X, but it's not necessarily path connected anymore because when you pull things back, they might not be path connected, but what you end up getting has path components. So you can therefore say that this is equal to a union, let's say Vi over some indexing set. These are the path components. And as we remarked last time, if you assume that your spaces are locally path connected, then the path components happen to be open subsets of X, so that's just something nice to know. And if we write this, then then pi maps each Vi homeomorphically onto U. So that's the definition of a covering map. So let's maybe write down a very simple lemma that we'll use. So we're going to talk about some properties that covering maps have. So let's begin with a lemma. For lack of a better name, I'm going to call this the shrinking lemma, as you will see. So the lemma says this, that if pi from X to Y is a covering map, and U in Y is evenly covered, then if U prime is another open set in Y, and U prime is sitting inside U, then U prime is also evenly covered. So this is called the shrinking lemma, and the proof of this is quite simple. So let's write a formal proof for this one. Well, we can maybe even draw a picture. Hopefully a picture will help. So let's see, maybe we draw a picture down here. So the idea here is, let's say this is X, this is Y, and you have some U over here. And because this is a covering map, so I have some map over here, pi, when you pull back U, you get pieces over here. So I'm just going to draw 3 of them. You have 3 path components in X, and each of these 3 path components gets mapped homeomorphically to U using this map. So if you pick something smaller and you pull it back, well, it's going to get, so you get these 3 pieces, and the smaller piece will just give you a smaller piece over here. So you basically get 3 pieces over there. And each of these gets mapped homeomorphically to the blue one because pi is a homeomorphism on the larger one. If it's a homeomorphism between this red one and that red one, it will certainly be a homeomorphism if you restrict it to something smaller. So I guess we do not even have to write a formal proof. I think this picture is convincing enough. So this is what we call the shrinking lemma. And what I want to get to is this first property. So let's make another definition. So let pi from X to Y be a covering map, and P be a point in Y. The set pi inverse of P. Well, if you want to be a little bit more precise, you really have to say it's the inverse of a set. So it's the inverse of the singleton set. So you're pulling back a set. But we usually get sloppy and we just say the inverse of a point. So this is, of course, the set of points X in your space, so that pi of X is equal to P. This set is, of course, non-empty because this is a surjective mapping, is called the fiber of P. So the fiber of a point is when you pull back a point. It's very similar to when you pull back an evenly covered neighborhood. The distinction here is, of course, you're not pulling back an open set, you're just pulling back a single point. But other than that, it's a very similar idea. And here is our first interesting proposition, that all fibers have the same cardinality. So what this means is, if you take a point in Y, it does not matter which one, if you pull it back and you get 6 points in the fiber, in other words, 6 pre-images. Okay, so maybe we draw a picture over here. So if you have a point P and you pull it back, and let's say there's 5 pre-images, then if you were to pick a different point, P prime, there will also be 5 pre-images. You cannot have a situation where you have a different number. And it's the same thing. It also works if you have an infinite amount of them. If, let's say, you have a fiber, if you have an infinite fiber, let's say countably infinite fiber, then a different point will also be countably infinite. So that's why we say the same cardinality, and we do not say the same number. There's the same number of pre-images in a fiber because it might be an infinite number. So that's why it's a little bit better to say the same cardinality. So let's give a proof of this. And before we give a proof, maybe we make a definition here. We say pi from x to y is an n-sheeted covering if and only if all fibers have n images. So based on this proposition, you only have to check a single point. You do not have to check all of them. And if at a single point you have n preimages, then all of the points have n preimages, and then you call this a finite covering. You can also call this a finite covering. But by saying n-sheeted, you're being a little bit more specific about how many preimages you have. So let's discuss how we prove this. Okay, so we're going to prove the proposition that all fibers have the same cardinality. So here is a proof of this. And I'm going to do this proof in various stages of generality. So I'm going to start with this one. So assume, so here's what we want to show. So we have to pick P and Q in Y. And we need to show that pi inverse of P has the same cardinality as pi inverse of Q. So this is the notation that we use in set theory. We put norms around the two sets and we equate them to each other. And what this notation means is that we do not necessarily assume that this is a finite number. This just means that there's a bijection. All this means is that there's a bijection. There's a bijection between these two. So assume for now that there is an evenly covered open set U, so that P belongs to U and Q belongs to U. In general, that's not going to be true, because what you're saying is, to draw a picture, this is P, this is Q, and in general, you have an evenly covered neighborhood for this one, and you have an evenly covered neighborhood for that one, but they will usually be different evenly covered neighborhoods. If you have an evenly covered neighborhood for P, that's not necessarily an evenly covered neighborhood for Q. That is not necessarily guaranteed to hold. But let's assume that you can find a single open set that works for both of them. So then you can find a U like this, and then you pull it back. Okay. So now when you pull it back, you get these preimages, right? These pieces that are being mapped homeomorphically. So every single one of these is being mapped homeomorphically to U. And because they're being mapped homeomorphically, we have a bijection between this one and this one. So that means there's exactly one point in here that gets mapped to P. Right? So there's exactly one point over here that's being mapped to P, and there's exactly one point in there that gets mapped to Q. And then the same thing can be said about all of the other ones. And so what that would mean is the number of preimages for P and Q is equal to the number of path components that you have when you pull this back. So to write out the details is you would say this. So you would say you're going to write pi inverse of U as a union of VI. The indexing set could be infinite, that's okay, as path components. And then since pi is a bijection, so since pi, so if you take pi and you restrict it from VI to U, so of course, the pi in the beginning, this is the global map on all of X, but when you restrict pi to one of these path components, you have a homeomorphism. So since this is a homeomorphism, there is exactly one point, let's call it pi in vi, so that pi of pi is equal to p, and a qi so that pi of qi is equal to q. So there's exactly one pre-image in this ith path component, right? So you have a one-to-one correspondence. And, well, I should say this. Well, okay, maybe I should just complete the proof by saying, so thus the cardinality of this set is the same thing as the cardinality of the indexing set. Because when you pull back P, these are exactly all of the ones you get, the PIs. So the collection of all of the points that get mapped to P are exactly these PIs, but every single one of them is coming from VI. So you can index them using this indexing set I. And the same thing is also said with the other one. So this would be also I. And then from here, the proof would be complete. Both these therefore have the same cardinality. But of course, what if this assumption is not true? What if these come from, well, you see, we're assuming you can find a single open set that evenly covers both of them. Now, more generally, so now let's be a little bit more general. More generally, let U, so this is going to be an open set in Y that contains P, be evenly covered. And let's say U prime, this is open in Y, this contains the other point, also be evenly covered. So now we are assuming that you have two different openly covered neighborhoods around P and Q. So let's assume, so we're going to make another assumption just to make the proof a little bit easier. So now let us assume that U intersect U prime is not empty. So here's a picture to help see what's going on. So here's P, here's Q. We find an evenly covered neighborhood U. We find another evenly covered neighborhood V. I'm sorry, not V, U prime. And we're assuming that they intersect. So because they intersect, they have a point in common. So for lack of a better name, let's call this point Y. Y be a point of intersection between these two. So they have a point of intersection which we're calling Y. And now here's what we can do. By the special case, we know that the cardinality at the cardinality of the fiber of P is in bijection with the cardinality of the fiber of Y, because P and Y are part of the same evenly covered neighborhood. And then you just repeat it again with U prime. And pi inverse of Q is in bijection with pi inverse of Y. And then you put it together and you've proven that these are therefore in bijection with each other. But what if this is not true? So that's, I think, be interesting to put that as a homework problem. So basically, this is what you're going to do. You're basically going to say, like, in general, this is what's going to happen. If this is P and this is Q, you have, let's say, a neighborhood over here, U, and you have another neighborhood over here, U prime. What if they do not intersect each other? So because we're assuming that our space is path connected, we can draw a path between P and Q. And so the reason why I do not want to write out the details of this proof is because this proof uses a bit more point set topology, and this is not a class on point set topology. But basically, just to give you an idea, there's a path. So you're going to pick a path f from 0, 1 into y. F of 0 is P, f of 1 is Q. And here you have to know some point set topology. You have to know that the image of this path is compact. So this is a compact set, so its push forward is going to be some compact subset of y. So this is going to be compact. And this will allow you to create a finite chain. So you're just going to create basically like a finite chain of neighborhoods that are all sort of like linked together until you get to the one that you want. And you basically repeat the argument at each step. You can always find a point in between these two, somewhere along the path, and then you just reapply the argument over and over again because they keep on intersecting on every level. So this is sort of like a special case when the two evenly open neighborhoods intersect. And now to make it a little bit more general, if they do not intersect, then you just have to argue that you can create like this chain of neighborhoods that keep on intersecting, and they take you from P to Q. And you can create a finite such chain because of compactness reasons. So I think maybe that would be a better homework problem because that's the main idea, and you just have to figure out a way how to make it into a formal proof. But at least this is like the formal part of the proof, and then you just have to continue it forward and generalize it. But I think that's enough about that. So another thing that I wanted to mention is this is another proposition. So this is another property of covering maps. If pi from x to y is actually, before I write this down, the previous proposition is not true if the spaces are not assumed to be path connected. So let me show you what I mean. So let's say y is a union of two disjoint circles, and x is a union of two disjoint circles. And the covering map from x to y, so let's say this is the covering map. This is sort of the z cubed covering map that we talked about, where you have a point here and you have 3 pre-images, and then this is sort of the squaring map where you have a point and you have 2 pre-images. And now you can see that it's a covering map. However, the fiber of this point has 3 pre-images and the fiber of this one has 2 pre-images. So it's actually important that these spaces are path connected. Otherwise, it's not going to be true. So if you add that assumption, then when you construct the path between the 2 points, you actually need that assumption of path connectedness to make this work out. So anyway, so here's our proposition. So if pi is a map from x to y is a covering map, and x is compact. So here we assume that the reader, the audience, is familiar with what it means to be compact. If not, you can probably ignore this proposition. It's just some extra point set topology. But if x is compact, then pi is a finite covering. Okay, so let me just say what the assumption here is, as we've said. So we assume that spaces are path connected, locally path connected, and we said you can also assume that they're Hausdorff. So in this proposition, we're going to use the Hausdorff assumption. I think we only need the Hausdorff assumption on x. But again, in practice, the spaces are going to be Hausdorff anyway. So here's an outline. I do not want to spend this video lecture going over the proof because that would be too much point set topology. And rather what I would show you is the idea of how to prove it and then put it on the homework and you try to prove it yourself. It's actually not that hard. And I'm going to give you two versions. So on the homework, you will have two versions of this proof. One of them will use a point set topology. And the other one's going to be more concrete. You're just going to prove it in Euclidean space. So it will be, I guess, even more elementary if you're not comfortable with point set topology. So I'll give you both versions because, as I remarked, you can assume that x and y, in most cases, are just living inside Euclidean space. So here's the outline of the proof. So you're going to observe that if you pick a point in y, then pi inverse of p, if you pull back the point, the fiber of the point, this is a discrete subset of x. So what does this mean? It means that for every x in the fiber, there is an open set in x, so that v intersect pi of the fiber is just x. So that's what it means to be discrete. So the intuition is discrete is when you have a bunch of points and they do not come together. So when you're saying that something is discrete, around every point you can find v, so that v only contains that point and nothing else. And this just follows from the fact that this is a covering map, because given this point in y, you can find an evenly covered neighborhood, and this v is one of those path components. When you pull back the evenly covered neighborhood, it will only contain that point and nothing else. So you can therefore draw a small enough open set that just contains this point and nothing else. So in some sense, all of these points are separated away from each other. So that's what it means to be a discrete subset. Right? This just immediately follows from the definition of what it means to be a covering map. So the fiber is a discrete subset of x. Now, since y is Hausdorff, so I guess we need to assume that y is Hausdorff. Well, let's just assume they're both Hausdorff. Since y is Hausdorff, the singleton point set is a closed subset of y. And so when you pull it back, when you pull back something that's closed, you pull it back, this is a closed subset of x. Okay, so that's a closed subset of x. This is just continuity. When you pull back a closed set, you get a closed set. So this is a closed subset of x. Now, since x is compact, pi inverse of this is also compact. Right? It's a closed subset of a compact space. So here's the Euclidean version. If this bothers you, this Hausdorff and compact stuff, if that bothers you, so here's like the Euclidean version. So if you just imagine that these are regions in Euclidean space, a single point in Euclidean space is a closed set. Okay, so you have a closed set. When you pull back a closed set, you get a closed set. So this is going to be some kind of closed subset of x. And now in like advanced calculus, in real analysis, you've probably used the Heine-Borel theorem a bunch of times. So if you're assuming that it's compact, it would mean that this is a closed and bounded set. Just a small little warning, closed and bounded does not make sense in general topological spaces. Boundedness is not a topological notion. But in Euclidean space, that makes sense. So basically, this is compact, and this is a closed subset of it. So this is bounded. It's also closed because it's a closed subset. So this is also compact. So whatever this is a compact subset of that. And now the whole point is, and now use the fact, okay, and then basically it's this. So, and then you observe, so pi inverse, so this fiber is both discrete and compact. So it must be finite. Sometimes, so if you're comfortable with, so to go back to advanced calculus, basically you learn about this thing called the Bolzano-Weierstrass theorem that you probably use a lot. So if you have like an infinite collection of points, so let's say that it was infinite. Well, it's compact. So that means it's bounded. It's sitting inside, let's say, some rectangle or something. It's in a bounded rectangle. And so that would mean if you have an infinite amount of points, they have to accumulate somewhere. So it cannot be discrete. That's the idea. This is what you call the Bolzano-Weierstrass theorem, because if you have an infinite number of points, you have a sequence of points, and that sequence of points has a subsequence that will have a limit somewhere, and whatever limiting point that is, it would violate the fact that it's discrete. Everything will sort of accumulate around the point, but it's not supposed to because it's discrete. So that's basically the idea. So hopefully you find that fairly convincing. I do not want to write out every single detail and turn it into a point set course. But that's the argument, like the main idea behind the argument for why this works. Now, let's remove this and let's talk about this. So this is a question: is the composition of covering maps another covering map? So the question is basically this. Let's say pi from x to y is a covering, and pi prime from y to z is a covering. So the question is pi composed pi prime, so this is going from x to z directly, also a covering? So let me see if I've written that the correct way. So x goes first, pi prime goes second. So this is written the correct way. So is this a covering? So let's try to prove it and then see what we need. So let's try to prove it. So let us try to prove it. So to show that pi prime composed pi is a covering, we pick some point, let's call it z, lowercase z, in large Z, and we need to construct an evenly covered neighborhood. That's the definition of what it means to be a covering map. So the mapping, this composition from X to Y, we have to be able to find a, well, I guess we skipped the part where you have to show that the composition is surjective, but that part is trivial. So we pick a point in Z, and we have to construct an evenly covered neighborhood around the point. So let's try drawing some pictures to see what's happening. So let's say we have this point Z. Now, what do we know? We have to use what we know. So we know that pi is a covering and pi prime is a covering. So we pick a point Z, and since this one is a covering, we can construct, so we can find, right? So we can pick an open set, let's call it U, an open set U in Z that contains this point. It's path connected, and when you pull it back, pi prime inverse of U, you will get a union of path components, Vi, where Vi are now open sets in Y, and pi prime maps each Vi homeomorphically onto U. So the picture here is you're going to construct an evenly covered neighborhood U, and then you're going to get this stack of pancakes. Let's say this is Vi, where every single one of these is now being mapped homeomorphically to that U. Now, because you have a composition, right? You're doing a composition. So you just did pi prime, and now you have to do the other one. You have to pull this back. So you have to take every single one of these, and you have to pull them back. But the problem is that how do you know that these are evenly covered neighbors? So maybe what I should do is, when you take this point Z and you pull it back, you have the fiber points. So you have a point in every one of these that's being mapped to Z. So maybe what we can do is, maybe we should say this. So you're going to pick Yi in Vi so that pi prime of Yi is equal to Z. So those are like the fiber points. And now you want to use the assumption, the other given, that this is also a covering map. And these are open sets in Y. But here's the problem. How do you know that these VIs are evenly covered themselves? So you do not know that. So rather, what you do is you have to replace them by something smaller. Okay? So what you would do is this. You're going to, so since pi from X to Y is a covering, for each Yi in Vi, we can find a smaller set, let's call it Wi, contained in Vi, that's containing this point Yi. So this is where we're using the shrinking lemma. Actually, yeah, so maybe I should not skip. Yeah, maybe I should not skip ahead. So since each is a covering for each Vi, we can find, so let me not do that yet. So for every one of these points, we can find an evenly covered neighborhood. Let's call it Vi. Vi does not, I'm sorry, Wi. Wi does not have to sit inside Vi. But the point is that such a neighbor has to exist because this is a covering. We can find an evenly covered neighborhood Wi. So this is an open set in Y with Yi also being in Wi. And now the point is, by the shrinking lemma, we can replace, if you have an evenly covered neighborhood, you can always replace it by something smaller. Okay, so by the shrinking lemma, and the locally path connectus property, we can find an even smaller set. Let's call it Vi prime, that's sitting inside the intersection. You need to understand that Vi is path connected and Wi is path connected. But if you take two path connected sets, they do not have to be path connected. So here's like a very easy example. Notice that this is a path connected set, that is a path connected set. But when you intersect them, this piece on which they intersect is no longer path connected. So this is not necessarily path connected. It contains the point, but it's not necessarily path connected. But by the local path connectus property, since it contains the point, you can find something smaller that is path connected and sits inside it. And because it sits inside it, it's sitting inside Vi, which is evenly covered. So by the shrinking lemma, Vi prime is also evenly covered. So we can find a Vi prime, which is path connected, and contains, of course, this point, and is evenly covered. So the original set, Vi, might not be evenly covered, but you can replace it by something smaller that is evenly covered. So let me modify the picture so you can construct something smaller that is evenly covered, and you can now do this around every single one of these. But here's the problem. The problem is that when you start mapping these blue sets, well, before I say that, what are we trying to show? We're trying to construct an evenly covered neighborhood. We're trying to find just one. That's the property of being evenly covered. We have to find one, a single open set U that contains the point and is evenly covered in the composition. But look at what we're doing. We're creating infinitely many different sets. We're no longer having U, because every single one of these, when you map them back to U, they're going to give you different sets. So you're going to have one that goes like this, you're going to have one that goes like this, you're going to have, they're going to be contained in U, but there will be different sets. You're going to have different ones. So what do you do about that? So if we assume, so let us assume that the indexing set I is finite. So we have what is known as a finite sheeted covering. We're trying to find a single open set that will do it for us. Each of these is evenly covered. Okay, so let's assume that the indexing set, so we have a finite number of sheets. So this is what we do. We map each of these sets back into U. They're going to be open. So then pi applied to each of these sets, Vi prime, is an open subset of U. So they're all open subsets of U. And they're all evenly covered. They're all evenly covered because, well, it's the shrinking lemma. They're all sitting inside U. The reason why they have to be open subsets, if you're worried about the fact that you're pushing forward an open set, you need to understand pi is a homeomorphism on every single one of these. So it pushes open sets to open sets. So they land in, they're all open subsets of U. And they're all evenly covered by the shrinking lemma because you're taking something smaller. U is evenly covered. So each of these is evenly covered. And since you're trying to find one single set that works for all of them, the reasonable thing is to sort of intersect them all. This is why you need it to be finite. So now set, let's call it U prime. This is going to be the intersection of all of these blue ones. This is going to be the intersection of pi of Vi prime. So then this contains the point because they all do. individually they all do. And U prime is an open set in Z, because it's a finite intersection of open sets. Finite intersection of open sets. So it's therefore going to be open itself. So then, okay, so then we claim that U prime is an evenly covered neighborhood for the composition map. And the reason for this just has to do with the fact, well, maybe, I mean, I want to be lazy. I do not want to write it out because I kind of think written out the main idea. So I'll be lazy. I'll just say then U prime is an evenly covered neighborhood, because you see, what happens when you do the composition? When you do the composition, so if you pull something back using so basically we have this. We have X, Y, Z. This is pi prime, and this is the composition. So if you have a set over here, U prime, and you pull it back, you first pull it back using pi prime, but pi prime pulls it back into pieces, all of which get mapped homeomorphically to that U. But what do we know about these blue sets? The assumption now is these blue sets were constructed to be evenly covered themselves. So now if you take every single one of these blue sets and you pull them back again using the other map pi, then they're being pulled back, right? Every single one of these gets pulled back to evenly covered pieces. I should say components that are homeomorphic to that. So then the composition would be a homeomorphism on every single one of these, right? You go like this, then you can go this way, you can go that way, and so on. So, I mean, the whole idea works because you took every single one of these, you mapped it into here, and then you intersected it. By intersecting it, you sort of descended down on the smallest thing that you need in order for work. So what you can see here is we are assuming that we have a finite sheeted covering on the first, well, on the pi prime covering, on this one. So let's write this as a proposition. Proposition. So if pi from X to Y is a covering, and pi prime from Y to Z is a finite covering, then the composition, wrote that backwards, from X to Y, is a covering. So that's what we just proved. And you may wonder, do you really need this? And the answer is yes, you need this. Without the finite covering assumption, you can come up with a very, very bizarre example of two covering maps. So they will both be, yeah, well, the second one has to be an infinite sheeted covering. You can come up with an example of covering maps whose composition will not be. And I'm going to show you this example so you get to see it. I think it's a very interesting example, and you see a nice example of a covering, but it's kind of bizarre, but I think it's just nice to see this example. Now, this is a very bizarre example, as you can see. The space at the very bottom, this one down here, this one is called the Hawaiian, I'm not sure how to write Hawaiian, earring. Basically, what it is that you have a circle, and then you have another circle, and then you have another circle, and they keep on diminishing down to a point, but there's an infinite number of circles. So that's what we call a Hawaiian earring. And I was able to find this picture on a Math Stack Exchange site, where someone was nice enough to draw a picture for this example. some of the sources for this example, or similar examples, they sort of just write things out without really showing you the picture, and then it's hard to get an idea of what it is. But this makes it a little bit easier to understand the example. But even this example is fairly confusing. So let's go through this. So we have three spaces over here. We have, let's say this is X, this is Y, and this is Z. And we have covering maps. I think it's easier to first look at this covering from Y to Z. This one's easier to explain. So basically the way this works is you have this outside circle, and as we know, there's a covering of the real line, so that's like the real line, that's being mapped to the circle. So we know what that one is. And the other ones are just being repeated. So this one right over here is just being repeated along the way. So let's say you have a point. So if the point is on the red one, then you use the exponential map to map that point to wherever that is. So maybe it'll be over here. And then this point will be mapped to the same thing, and so on. So this will be sort of like the pre-images of that point. And these circles, I would say, are self-explanatory. They're just being mapped to this one, and then the inner circles get mapped to the inner circles. So that is you have to check that this is a covering map, but the basic idea here is you have to see if you have you have to check whether or not this mapping has evenly covered neighborhoods. So let's pick something very simple. Let's say we pick a point all the way here on top. So if you have a little arc over here, well, that point, its pre-images would be here, because the outside circle, that's coming from the real line. So this is the outside circle, that's coming from the real line. And then you have these, so these are being mapped homeomorphically to that arc. Now let's say instead we pick an arc over here. Well, that arc comes from these ones, so these are mapped homeomorphically to that arc. That makes sense. So the one that is a little bit suspicious is about this point where all infinite circles come together. So let's see what happens there. So if you draw a little neighborhood, here's the way the little neighborhood is going to look like. You're going to have a piece of it. So you have to sort of imagine you're drawing like a little disc and seeing how it intersects. That would be the little neighborhood. So you have this arc, you have the point, then you have this arc, then you have this arc, you have that arc. But because the circles get infinitely small, at some point you're going to see the circles again. So a neighborhood of this point will consist of a finite number of arcs and an infinite number of circles. So how would it look like in the picture? So in the picture, this point is coming from here, right? So that point will be coming from, so this will be the pre-images of the point. And if you draw a little neighborhood, then you're going to pick up this piece, you're going to pick up these pieces, and then you're going to have a repetition in the picture where, so basically what we're saying is, when you draw a little neighborhood over here, right, a little neighborhood, you get a finite number of arcs. So let's say you get 4 arcs, and then you get your infinite collection of circles. That's how it looks like locally. In these ones, this outside circle, the big circle, it's appearing as this the line, this horizontal line that goes across. So this very outside arc from the big circle, it is homeomorphic to these vertical lines that go across. And then the remaining number of arcs that you see in that little neighborhood would then match the number of additional arcs you see over here, and the rest will be the infinite collection of circles. So locally, we can find an evenly covered neighborhood. So this mapping from Y to Z is a covering map, and it has an infinite number of fibers. So this one I think is a little bit easier to explain. The second one is harder to explain. So let's explain what's happening here. So this one is, let's write infinite sheeted. And the first one, this is going to be double sheeted. So how does it work? Let's maybe we should start. So I think it would be helpful to start with this one. And I think that this circle is unnecessary. So delete this circle. Yeah, just delete this circle. Let's try to understand. So pretend that circle is not there. So you have this line, and then you have a copy of this line up here. So let's talk about what it does on the vertical, on the horizontal lines. This is sort of easy to understand. So both of these points, they just get projected down. So this point and this point, they both get projected down. So they just go, that's just a projection. So that makes sense. Now, what about this point over here? Well, on this circle, I think you could probably guess what it's doing. These 2 points, they're both being mapped to that circle. So because it's the same circle in both pictures, but there's 2 copies of the circle, both of these points, they get mapped to that one. So this is why I do not like this extra larger circle on the outside. I think it creates confusion, and I think it's unnecessary, because then it's not clear where are you mapping this blue circle to. So you just do that. Okay. If you have a point right there, then that one and this one, then they're both being mapped to that one. So this is why we want it to be double sheeted. Now, in this picture, this one looks a bit confusing. So as before, pretend this is not here. Just delete this away. Yeah, just delete this whole thing away. So here, the idea is that this outside circle is being opened up into a larger circle. That's the idea. You're opening it up into a larger circle. But the inner circle, this one, it's just like before. These 2 points, so this smaller circle and that smaller circle, they both get mapped to the smaller circle, but this outside circle, you're just opening it up. It gets opened up like that. So then there's 2 pieces of it. So if you have a point on this one, it's going to be here. And it's going to be, yeah, and it's going to be here. So yeah, that's what you're doing. You're just taking this. I mean, you see, you have a circle over here, and you can open it up like this, and then you open it up again. So you have 2 copies of it, and you just open it up into an arc. So you have both of these that go to it. And now with this one, what you do is the outside one. So as before, the circle on the extreme outside, the one right over here, you just delete it, pretend it's not there. And the circle on the outside, just like before, it opens up into 2 arcs like this. And the circle that's the one that follows it can also be opened up, but this is the one that kind of goes inside it. And then the remaining circles, they sort of remain the same. And the whole idea is, because you have an infinite number of circles, you can just keep on opening it up. That's the whole idea. You can just keep on opening it up. So now you open up 3 circles, you open up 4 circles, and so on. So that's the idea. You just keep on opening it up. Now, it makes sense as you're going towards the right. As you're moving towards the right, you're just taking circles that are inside the Hawaiian earring, and you keep on opening up one after the other. But what do you do when you go to the left? What are you doing? So this is what I think is what you can do. You can just, the picture that we drew over here, you just leave it. You do not do anything with it. So this picture that you have here, you just keep it and you just repeat the picture again. So this is just going to be, so to fill in the picture, you're just going to have this circle going like this, Hawaiian earring, and here you have another Hawaiian earring like this. And you do not add this line, you do not add it, you just leave it like that. So when you're going towards the left, you're not really doing anything. You're just repeating the same. You're basically using like a very boring type of a map where you're not doing anything. But it gets more exciting as you go towards the right. So as you're moving towards the right, you just keep on opening up a circle after a circle after a circle. And you then have to carefully check that this is a covering map. So you have to check that is it true that you have evenly covered neighborhoods. So let's see if this works out. Let me just remove all of these. So you pick a point anywhere in this picture. So let's say you pick a point, let's say right there. Okay, so let's not pick the point where infinitely many things happen all at once. So let's pick the point here. This point will correspond to, it will have two pre-images. So it's this one and that one. So as we said, this very outside circle, it's not that one. So this circle opens up. And if you have a little arc that you drew, then you have two arcs. And you can see those two arcs are the ones that are being mapped homeomorphically to that arc. Likewise, if you had a point here, then you would, and you drew a little arc, then you would find that arc on this one and on that one. So there you have the two arcs that are being mapped homeomorphically to that arc. Okay, and then the same kind of argument can be applied here as well. If you pick a point here, then the pre-image of that point, it's just this one. And if you draw an arc, you see it here. And with this one, if you pick this point, you only see these two, and you have this one, and that is it. So again, this outside circle, I think it's unnecessary. And it's also unclear how the mapping is defined in the outside circle. So you can see it satisfies the evenly covered neighborhood as long as you stay away from that infinite point. So now let's see what happens at the infinite point. So let's say we pick the infinite point right over there. Then in our picture, we see this, okay? And if you choose a small enough little neighborhood, right, a small enough little disk, then what do we see? We see what we said before. You see an arc, right? And then you see a finite number of pieces that are going like this. And that's exactly what you see over here. Oh, so I realized, yeah, I realized a small mistake. I realized that this outside piece is actually necessary, so sorry about that. Yeah, it has to be mapped, of course. It has to be mapped to the one that connects it, of course. And then the one on the left is being mapped to the same thing because it has to be, yeah. So of course it has to be that one. So because you see, we're not saying what the pre-images of this one is, so it has to be this one. And then as you go towards the left, what I said remains true, that you're just repeating the picture. You're not doing anything when you're going to the left. It's just going to be the exact, yeah. So these extra circles are actually necessary because you have to say how you get the horizontal lines. Oh no, sorry about that. I'm confusing myself. Yeah, it's I completely forgot for just a moment that the points on the horizontal line are actually coming from up here and down here. So yeah, it's not necessary. So we have this, and the point here is what happens. So the mapping from the top to the bottom is not a covering map for the following reason. If you pick a little neighborhood, here's what you see. You will see, that would be your infinite point. You would see a finite number of arcs, let's say 3, and the rest will be circles, right? Now, here's the whole point of this, that as you go towards the right, the circles keep on opening up. So eventually, the neighborhoods of that point, as you go, you will eventually get to a point where you will have a certain number of finite arcs, but where you're supposed to have that circle, it opens up right? You can see you keep on opening up the circle. It opens up. And so you will have an extra arc, right? You will have an additional arc that you did not have before. So you still have an infinite number of circles, but you will have additional arcs. And the point is, no matter how small you try to make that neighborhood, no matter how small you make it, because as you're moving on the right in this space, as you go further, further, further out, eventually every single one of those circles gets opened up. So you start to see neighborhoods that are not homeomorphic to the neighborhood that you drew in the very beginning down here. So, and that's why the composition is not a covering map. So a very interesting example, but that is a pretty ridiculous example to come up with. So whoever came up with this example must have been really, really, really smart. But now let's return back to more basic examples of covering maps. The next property that we want to look at is a product of covering spaces. Or maybe we should say the product of covering spaces. And the proposition is fairly simple. It goes like this, that if, let's say, pi1 from x1 to y1 is a covering map, and we have another covering map, then if you take the product of the two maps, so I'll explain what that means, from the product space to the product space is also a covering map. So we have to define what we mean by the product of two maps. And that's sort of defined the obvious way. One way of defining the product of two spaces is as a Cartesian product. It's a set of pairs where you put the product topology on that. So where pi1, pi2 apply to a pair, A comma B. So here, A comma B, that's a point in the Cartesian product. So this is equal to, by definition, so this is how we're defining the product map. This is equal to, by definition, you apply pi1 to the first coordinate, you apply pi2 to the second coordinate, and then you put them as a pair. And then you need to understand that pi1 of A, that's an element of y1, pi2 of B, that's an element in y2, and together that pair is now an element in y1 product y2. So you've just constructed a map between these two. It's not difficult to check that this is a continuous map. It's a surjective map, and it will satisfy the properties of a covering space. Also, if you have two spaces that are path connected, their product is path connected. If they're locally path connected, their product is locally path connected. So all of those properties, they go through. It's tedious. It's not that exciting. And I think that this would probably make a good homework problem. It's not really much to be said about this, but it'll make just a nice problem on the homework for you to think about, just carefully going through the definitions. So as an example, you can generate a new covering. So here's an example of this. So let pi from the real line to the circle be the exponential map. So pi of x of a real number is e to the 2 pi ix. And as we remarked, we're using the funny notation where we have two different meanings of pi, but we understand that we're mathematically mature enough to tell the difference. So let's call this x1, let's call this y1, and let's call this pi1. And then we just repeat it again. We'll use the exact same map, but using different notation, we can call this pi2, x2, and y2. And so based on our proposition, so if you take the product map, let's call it F, from from R2 into S1 cross S1. So we're just doing the product map. So instead of calling it pi cross pi, let's just call it F. This is R2. This is a product of two circles. So defined by that f of x comma y of a point in R2 that's equal to a pair of complex exponentials is a covering. So what this shows is that the plane is a covering space of the torus. So this is one of the ways you can describe a torus. So this is, of course, homeomorphic to the torus. This is not exactly something you can visualize, because if you were to write this out, S1, this would be points in the complex plane whose norm is 1. So then you would say that a product of two circles will then consist of pairs of complex numbers with the property that both of their norms is equal to 1. The issue, of course, is that a complex number is usually visualized as a point in the plane. So this is two real coordinates, and this is two real coordinates. So really, whatever this is, it's visualized as sitting in four-dimensional space. So you cannot really visualize this. So this is not something you can visualize, but that's okay. This is one of the ways we think of the torus. The way that we typically think of the torus as a donut-shaped space, that way of thinking of the torus is often not convenient for topology, because then you have to write out the parametric equations for that donut shape, which is not very convenient. It's a lot more convenient to recognize that the torus is a product of two circles. If you've never seen this before, this is a fairly common way of getting a torus. We're actually going to show a different way of getting a torus, and that's just something we need to get used to, that anytime we talk about the torus in topology, we're not referring to any one specific way of describing a torus. We just are referring to all different topological spaces that are homeomorphic to each other. So there's multiple different ways of describing a torus. This is just one of the ways, and depending on the kind of problem that you're doing, you pick one of these different ways of representing a torus. The way that you think of the torus visually is often never used as a way of describing the torus, because it's too inconvenient, because then you have to write out the parametric equations. So the reason why this gives you a torus, if you've never seen this before, here's a very quick explanation. So if you take the interval from 0, 1 cross 0, 1, you would have the interval going sideways, and then you'll have the interval going vertically, and when you fill out the space, you get the unit square. Now, if you take S1 cross 0, 1, then the way you can visualize that is you have the circle, right? You have the circle, and the extra coordinate ranges from 0 to 1. So this is at 0, then you draw it at 1. And when you fill in the space that's in between, you get a cylinder. So when you do S1 cross S1, you need to understand that basically the way you get the circle is you take the interval from 0 to 1, and then you glue the endpoints. So imagine that you're taking the endpoints of this cylinder. So this would be the endpoints. This is 0 and this is 1, and then you glue them together. So if you just glue them together, you put them together, then you end up getting this torus shape that you're used to. And this is why this space, at least intuitively, of course, one has to work out the details to show that it's homeomorphic to the concrete torus that we all think about, but I think this is fairly convincing that the space that you end up getting is homeomorphic to the torus. So what this example gives us is we have an example of a covering of a torus. And then you can use this property that a product of two coverings is another covering to generate many other examples. So now I want to get to, let's say this, so a source of many interesting examples. And this is going to be useful later on. So let's make a definition. Let X be a space, be a topological space, and ought of X. So these are the automorphisms of X. This is simply the collection of maps from X to itself. That's what an automorphism is. It's a map from X to itself, so that F is a homeomorphism. So this is called, so ought of X is a group under composition, under function composition. That's not difficult to check because the identity map, the identity function, will be a homeomorphism. The identity function is the identity for composition. And if a function is a homeomorphism, then it has an inverse function because it's a bijection, so you have an inverse function. And the inverse function is also a homeomorphism because that's what a homeomorphism is. The function and its inverse are both continuous. So you have a group. It's not necessarily a commutative group, but you have a group. And this is called the automorphism group. We call ought X the automorphism group of X. Now, actually, you have seen this before, but in a different setting. So this is actually very similar to the symmetric group. So this definition is very similar to the symmetric group. So this is what you see in an algebra class. So Sn, the symmetric group, this is called the symmetric group on n objects. So you can just assume that your objects are the integers from 1 to n. And what this is all bijections of this set, all possible bijections. You see, it's very similar to a homeomorphism, except when you're talking about the symmetric group, this is a discrete set. It's just a discrete set of items. So you're not worried about topology or anything like that. So you consider all possible bijections. But if you have a topological space, then it makes sense that you want all of your bijections to also preserve the topology as well. So you want them to also be homeomorphisms. So it's very similar, but you're adding a topological space. And also the difference, of course, would be is that the symmetric group is on a finite set, whereas the automorphism group in general will be on an infinite space. There's infinitely many points that makes up the space. But instead of considering all possible bijections, you want them to be homeomorphism because you have a topological space. So it makes sense you also want to preserve the topology. But it should be very similar to something you've seen before in an algebra class. So we call that the automorphism group. So let's make another definition. Let X be a space and G is a subgroup of ought X. So it's a, you can say this is a group of automorphisms of X. So we're not necessarily saying that G is all automorphisms, but it's some subgroup of automorphisms. So we say that G acts evenly on X if and only if for any, let's say, G in G, we can find, actually, let me take that back. For any point in X, we can find an open set in X. And let's assume that it's path connected, which we can always assume. Because if we're assuming that our spaces are locally path connected, anytime you have an open set containing a point, you can always shrink it further. So you can just assume it's path connected from the very beginning. So for any point, we can find an open set that's path connected containing the point, so that G applied to U, so this set, as you range over a group, is a family of disjoint. They have to be open sets, by the way. They have to be open sets because this G, what is it? It's an automorphism, right? So an automorphism, let's write it over here. So note that if G is in the automorphism, is in the group of automorphisms, so then it means that G is by definition an automorphism of X. So that would mean that if you pick an open set in X and you apply G to that open set, it's going to push it forward to another open set. So these are necessarily open sets. So the requirement is that these are all disjoint. Okay, so sometimes we call these the translates of U. It's not necessarily a translation, but that's just the way we sometimes say it. The automorphisms, they could be translations of your space, but in general they can do other things. They can be rotations, and in general you cannot even visualize them because you're working in an abstract topological space. But we just, nonetheless, the terminology we use is we call them translates. So the picture here is basically this, that if this square represents X, we're saying that if you give me a point P, you can find a small enough open set, so that would be your U, you can assume it's path connected, and if you apply every automorphism, so it moves this open set somewhere else. So maybe one of the elements moves it here, another one moves it here, another one moves here, like this. They necessarily have to be path connected because G is an automorphism. So if something is path connected, it will get moved to something that path connected. That's why we call them translates, because the idea is you're sort of moving them around, but not necessarily by a translation. That's just sort of just a way you want to think about it. That's not necessarily the way it looks like. So you're saying you get these non-overlapping pieces. So it's beginning to feel a little bit like a covering space property. So when that happens, we say the group acts evenly on your space. Kind of makes sense. It should remind you of a covering map. And what we're going to do is we're going to introduce a quotient. But maybe before I do that, maybe I should just give you some examples. So here's an example. X is the real line, and G would be the group of all, let's say, integer translates. In other words, i.e., so these would be, let's call them, so an automorphism. So this will be a map from R to R, so that the formula for this automorphism, it's an integer translate. It's X plus N for some N. Maybe it makes sense, instead of calling it G, let's call it tau for translate, subscript N, where N indicates the integer that you're using to do the translation. So tau of N applied to a point just translates the point by N. So clearly the identity map is translation by 0, and the inverse of a translation is translation by a negative. And if you have two translations and you compose them together, then you get a translation which is a sum of these two numbers. So what this shows is, so hence the group of all integer translations is isomorphic. So this is isomorphic as a group. It's isomorphic to the group of integers, right? Because as you can see, the way composition works, if you take two translation maps and you compose them together, that's the same thing as adding things together. So it's behaving exactly like the usual group of integers. So this, now, why does this group act evenly? So it is not hard to see that G acts evenly on the real line. Why is that? So here's what it has to do with. So here's the real line, okay? And you pick a point, P, on the real line. And now you're going to draw a neighborhood. So you're going to draw an open interval. Let's say its width is 1/2. So you're going to be, if it's sufficiently small, and if its width is 1/2, then let's see what happens when you apply various translations to it. So we're going to call this open set U. So now let's look at the translates of this open set. If you apply T0 of U, well, that's the identity. That's just going to be U. If you apply T1 of U, that's just going to take U and it's going to translate it over by 1. So this is going to be P plus 1. So here you're going to have P plus 1. And this is going to be 1/2. Now, notice that because this interval has thickness 1/2, and the center of this interval is moved over by 1 unit, but its thickness is 1/2, that means they're non-overlapping. And then you do it for all of the other ones. So you have to write out all of them. So if you write out all of them and so on, there's going to be an infinite number of them. But all of that infinite collection that you write out, you can see they're path connected subsets of the real line. They're open subsets of the real line, but they're non-overlapping. No two of them overlap with each other. So that's why this group, it acts evenly. This group acts evenly on the real line. Now let's give an example of something that does not act evenly. So we can call this a non-example. Let's suppose that G, this is the group of all translations. Not integer translations, but the group of all translations. And then G does not act evenly on R for a very simple reason, because here you have a point P. No matter how small you make that interval, there's a translation of arbitrarily small size. So let's say this interval has thickness 0.01. Well, you take a translation, let's say you take a translation of 0.001, so even smaller. And if you apply it to this open set, you just ever so slightly move it a little bit over to the right, and you can see that it will overlap. So no matter how small you make it, you can always find a translation that's even smaller, and when it moves it over, it will still overlap with the original open set. So this would be an example of something that is not evenly covered. I'm sorry, let me take it back. That would be an example of a group that does not act evenly on your space. Okay, so now let's introduce this definition. Let G be a group of automorphisms of X. So again, we're not saying that G is equal to the entire automorphism group. We're just saying that G is a subgroup of aught X. So we're going to do X mod G. So this looks a little bit funny because this is a topological space and this is a group. So usually when you have a quotient, you've definitely seen quotients in an algebra course where you take a group and you quotient out by a subgroup. You might have seen quotients in topology where you have a topological space and you have a subspace and you quotient out a space by its subspace. And now this looks a little bit funny because one of these is a topological space, one of these is a group, and you can still do a quotient. So here's the way it's going to be defined. This is going to be the set of, well, maybe before I do anything, I think this will make it a little bit easier. So for a point in X, let the class of P, and we sometimes write P mod G. This is simply the collections of elements in X such that X is something, it's G of P for some G. So this would be the points that can be obtained from P. So you pick a point, and then if you take automorphisms, different ones, and you apply it to that P, you get different points. And all of the different points you can get, you call that P mod G. And then you define X mod G to be the set of P mod G, where P is something in X. Okay. So you call this the quotient of X mod a subgroup G. And we're going to turn this into a topological space. So at the moment, X mod G is just a set. So maybe to give you an example, so hopefully this will make it a little bit easier. So going back to our example, X is the set of points on the real line, and G, these are the integer translates. So if you take, for example, take your favorite take your favorite real number, let's say square root of 2. Then square root of 2 mod G would consist of, it would be the set of all translates of that element. So you have square root of 2, square root of 2 plus 1, square root of 2 plus 2, and then you can go in the other direction, square root of 2 minus 1, and so on. So the terminology should make sense. It's very similar to when you talk about something mod, like you talk about integers mod a number. So it's very similar to that, except here we're working with a topological space. But other than that, it has a very same feel to it. And by the way, if you take square root of 2 plus 1 mod G, that will of course be the same thing as square root of 2 mod G. So because square root of 2 plus 1 and square root of 2, they can be obtained from an integer translate, they end up generating the same class, you would say, the same class mod G. And then you would say that R mod G would then be the set of all of those. So you will have the class of square root of 2 mod G. You have another, now you're not going to write square root of 2 plus 1 mod G because that's sort of repetitive, you already have that. But you can have, let's say, 0 mod G. So 0 mod G, this will be the, if you actually write this out, this would be the set of all integers. That would be the set of all integers because you start with 0 and you do integer translation, so you generate all of the integers. And now you pick a number you have not seen, let's say a half. So if you have a half mod G, if you write that out, that would be a half, 3/2 minus a half. So all integer translates of a half, and so on. So it's a infinite. So you see, it's rather complicated. It's what is this? This is a set of sets, or we usually just say it's a family of sets. That's what that is. So it's quite complicated because the elements that make it up happen to be sets themselves. But that's what that is. And what we want to do, so at the moment this is just a set, and we want to turn it into a topological space. So let's just discuss the setup again. So X, this is a space. G, this is a subgroup of the automorphism group. And X mod G, this is the set of all classes mod G, where the point ranges over X. So at the moment, X mod G is just a set. We want to topologize X mod G. So to topologize would mean we want to put a topology on this set. So a topology, a topological space, consists of a set of points, and you have a set of open sets. Now, we usually do not say a set of sets, so maybe we'll say a family of open sets. So there's two components that make up a topology: the points and the open sets. So at the moment, we have this. It's just a set. So we have described what the points are. So the points, right? So the points of X mod G are, you can say, classes mod G. So they're quite complicated. It's not like a single point. It's really a set of points all taken together. And now we have to define what it means to be an open set. So I guess this is the one instance in this course where it's not convenient to confine yourself only to Euclidean space, because what we're about to do, as you can see by looking at the quotient, you're no longer getting points in Euclidean space. You're getting something that's a little bit more abstract. And this actually shows the reason why it's very restrictive to confine yourself only to live inside Euclidean space, because you're limited by the kind of things you can do. The reason why topology is made more abstract than it is it gives you this extra freedom to do things that you otherwise would not be able to do. And this is like one of those instances. So, so here's how we're going to do it. So we're going to first define the quotient map. And we're going to use our favorite letter, pi. So this is going to be the map from X to X mod G. So how is it defined? It's defined in the obvious way. And actually, before we write anything down, this is like the funny thing about modern mathematics. This is like the difference between classical math and modern math. In classical math, there's not that many definitions. Things are a lot more elementary. But the proofs are rather complicated. They're messy. They require a lot of clever tricks. But in modern mathematics, the proofs and the definitions, the way you construct everything is usually done in the obvious way, like the first thing that comes to mind. Then what makes it hard? Well, what makes it hard is the definitions. You bury all of the complications into the definitions, into the abstraction. So that's what makes it hard. But the actual way of the way the proofs go, or the way you construct things in a proof go, they're often the obvious things to try. So there's an obvious map from X to X mod G. And what map is that? So if you take a point in X, you simply map it to its own class. Right? That's the obvious map. And this is clearly surjective. So now let U be a subset of X mod G. Now we're going to define what it means to be open. We declare U to be open, to be an open subset of the quotient topology, if and only if you're going to pull it back using pi, and you want this to be an open set in X. So that's the way you do it. So you define an open set to be something that pulls back to an open set. Now, this is reasonable because I think we want this map to be continuous. Right? This is sort of like an obvious mapping. So we want it to be continuous, but to be continuous only makes sense once you put a topology on this. So you have to put a topology. So to put a topology, you have to say what it means to be open. So you pick something in here, and you say it's open if you pull it back. So when you pull it back, it becomes open in X. So it pulls back to something open. Because this is exactly what you need to have a continuous map, right? Because a mapping between two topological spaces would be continuous if and only if for any open set over here, it pulls back to an open set over there. So you therefore declare a set in here to be open if it pulls back into something that's open. I mean, this is sort of forced on you in order to create a continuous map. And now this is not a very difficult exercise, but it's sort of boring. This is usually done in like a point set topology course. So one can check, and this is kind of boring, that this way of defining open puts a topology on X mod G. So the properties of a topology, if you have two open sets, their intersection is open, the empty set is open, the entire space is open, so on and so on. Not very exciting. Now here's the part that I want to get to. This is sort of like the big idea here. So let's say the setup. So we often assume that our spaces X are path connected, locally path connected. In fact, we often assume that they're Hausdorff. And sometimes, though not always, but sometimes compact. So when we're working with covering spaces, these are often the assumptions that we make. And I would say it's not just covering spaces, but the kind of spaces that one comes across in topology, especially when you're working with manifolds, as we will see later on in the course, that these are often the conditions that are satisfied. Now, if G is a group of automorphisms, then X mod G, so if you form the quotient space, will be path connected, locally path connected, and compact. That will always be guaranteed. And I'll actually prove it to you. So I'm going to prove to you this one, and I'll prove to you this one. Locally path connected, you can prove that yourself. So I'll just show you how it goes. It's actually quite simple. So you're going to start with the quotient map. Now, since X is path connected, pi applied to x is also path connected. You actually had that on your homework assignment, that if you push forward a path connected space, you get something that's path connected. But pi of x, the image of x, is exactly the quotient space, because this is a surjective mapping. And in the same way, if x is compact, then pushing forward a compact set gives you something that's compact, is also compact. And as before, pi of x is the quotient. So I just want to be a little bit careful here that I'm not saying that the quotient will always be compact. I'm saying that if the original space that you begin with is compact, then the quotient will be compact. Now, to show that it's locally path connected, that's not particularly that difficult, but you cannot necessarily use this mapping property. You have to do something a little bit more. It's not particularly that difficult, but you can try doing that yourself. Now, you might have noticed that the Hausdorff condition is not included here. And the reason for this is because the quotient may not necessarily be Hausdorff, but it will be Hausdorff if G acts evenly. So if, in addition, G acts evenly on X, then X mod G will be a Hausdorff space. This is not difficult to show. I think it's a great exercise. I'm going to just put this on the homework because that's the best way to learn. A lot of these things to check, they're very straightforward. They're kind of boring. You're not doing anything super clever, but you have to go through all of the definitions. So you have to go through the definition of what it means for a group to act evenly. You have to carefully remind yourself how the quotient space is made, and then you have to remind yourself what it means to be Hausdorff. But when you carefully go through all of that, you will see that the quotient will indeed be a Hausdorff space if G acts evenly. And you can try to think of your own examples when you get something more bizarre when the quotient, when the group does not act evenly. And I want to get to I would say the main, so what's the main purpose? So this is sort of the main purpose of quotients. This is like the reason why we're introducing quotients all of a sudden, is because they give us a lot of examples. They provide for us. So maybe I could make this as a proposition. Let X be a space, topological space. And again, the assumptions are that we assume it's path connected, locally path connected, Hausdorff. It might even be compact, but that's not required, so that we have such a space. And G is an automorphism group, and it acts evenly on X. So then the quotient mapping, pi from X to the quotient, is a covering map. So that would be a covering map. So first of all, if G is the space with the properties that we are assuming, then X mod G is also a space with the properties that we are assuming. But furthermore, the quotient mapping is a covering map. Why is that? This is actually very easy to check. So maybe as a proof, clearly pi is surjective. It remains to show that each point in X mod G has an evenly covered neighborhood. So we're going to pick a point in X mod G. But how does a point look like? Well, a point, it's a class mod G. It's an entire class mod G. Now, so P, so the P that we're using, this is a representative for the class. So this representative for the class, it's something in the original space X. Now, since G acts evenly on X, we can find an open set in X that contains the point and the translates are disjoint. We can, of course, always assume the open set is path connected. Okay, but how do we get, so how do we get a neighborhood in the quotient? What we ultimately care about is the quotient. So how do we get a neighborhood in the quotient? Well, so I think maybe a picture would be helpful. So this square represents X mod G, and this square represents X. And you have a point here, and around that point, you found an open set, and you have all of its translates. But you have this quotient map pi. So now, if you apply this quotient map pi to all of those, they will actually end up in the same thing. Right? They will all collapse down to the same thing. Why is that? So now observe. So then, if you apply pi to each of these open sets, that these are, so you're pushing them forward. These are open sets in the quotient. Right, so every one of these, you have a collection of open sets. You're applying pi to every single one of them, so you're getting open sets in the quotient. And then what you need to realize is you're going to observe that pi of G of U will actually be equal to pi of G prime of U for all G and G prime in your automorphism group. That you see, the whole idea is maybe this one over here is one translate, and maybe that one over there is a different translate, but because they're translates of each other, end up in the same class. That's what it has to do with. They end up in the same class. So they're different in X, but when do two things end up in the same class? So two things end up in the same class if they differ by a translate. So they end up in the same class. So they're in the same class. So that's why I'm kind of drawing it like this. They all sort of come together. Okay, so then if you apply pi to this collection, what is this? This is just one open set in X mod G. Right? So even though it looks like you might have like an infinite collection, but the point is, because these are translates of each other in the quotient, they become the same. They sort of they go into the same equivalence class. So they all really become the same. So this is just one open set in the quotient. Okay, so you give it a name or something. So call this O or something O. And then O is an evenly covered neighborhood of P mod G. Maybe if this makes it a little bit easier for you, let's say all of these blue points are points that are equivalent to P mod G. So they're different points, but when you apply pi, they end up in the same class. That's why they really come down together into the same point, because I mean, we are drawing a single point, but you have to understand that a single point is really a set of all of those points. So basically, yes, they're all different, but they're now part of the same set of points, and the same set of points is abstractly treated as like a new point in this quotient space. So they all come together, and all of these open sets, they come together into one, and this is an evenly covered neighborhood. And you can see why it's an evenly covered neighborhood, because when you pull it back under pi, you're getting all of these non-overlapping, right? Because this is the group acts evenly, so they're non-overlapping, and they're all being mapped homeomorphically over to that one. I guess the question is, why is it being mapped homeomorphically? But I mean, I'd rather not go there. I think we've said enough on this. That's sort of the main idea. And now that we introduce this fairly nice proposition, you can then use this proposition to generate a lot of examples. So now let's look at a lot of interesting examples of how you can use quotients to generate many different examples of covering spaces. Let us now look at a list of interesting examples of how we can use a group of automorphisms to generate a covering space. Let's start with this example, where this is what we saw earlier, where we start with the real line. So X is the real line, and G was the group of translations. These are integer translations. And we observe that the integer translations, they act evenly on the real line. And therefore, X, so we have a covering, pi. This is a covering map, where pi of a real number, X, is simply that real number mod the group. But maybe we can perhaps describe this covering in a way that's a little bit more intuitive. Let's look at this quotient over here and try to understand it. So let's begin by drawing the real line again. So this is the real line. And now if you pick a point on the real line, let's call it X, then the translations of the point are all equivalent to that point. This is X plus 1, X plus 2, X plus 3, and so on, X minus 1, and so on. So every one of these points is equivalent. So if you pick this point, then all of these other points, they become redundant. They're sort of being repeated. And all of these points that are in between are also being redundant. This point over here would then be equivalent to this one, and so on. So really the only part that is actually giving you a unique representative is somewhere between this interval. So maybe for simplicity, it's easiest to reshift everything back to the origin. So we're essentially saying that here we have the origin, here's 0, and here's 1. And 0 and 1, they end up in the same class, in the same equivalence class, whereas everything that's in between 0 and 1 is in a separate equivalence class. And when you go beyond that, you repeat. So these two have to come together. So maybe you can see what kind of a space that is. That would be a circle. So even though this is your covering map, this space is better thought of as the circle. I mean, in a complicated way, it's just a set of equivalence classes, but as a topological space, it happens to be homeomorphic to the circle. And so you really have a covering from the real line. So this is the real line. So you have a covering from the real line to the circle. And this looks like it's something we've seen before. That looks like it's the exponential map. So can we therefore say that this map pi is the exponential map covering? Well, almost. You have to be just a little bit careful. So more precisely, so let's just say this, that this example is not new. I mean, in a way, it is new because you have a new topological space, but on the level of homeomorphisms, you've not really genuinely created something new, because you have the real line, and you've just produced this map pi to the quotient, and we also have the exponential map to the unit circle. And when we're saying that it's basically the same thing we saw before, what we're saying is that there's a homeomorphism, there exists a homeomorphism between these two that will make this diagram commute, which would mean that if you go like this, if you follow the arrows like that, that would be the same thing as going like that. And let's actually write down what this homeomorphism is. So maybe we call it F. That's going to be our homeomorphism. And what is F doing? Well, it's quite simply, if you take a point on if you take an equivalence class, it would be some real number x mod g. And to get that point on the unit circle, you just map that point to e to the 2 pi I x. And the reason why F is a homeomorphism, it's because if you choose a different representative for x, you're just adding an integer. You're just adding x plus 1 or x minus 1. But because this function is periodic, so if you replace x by x plus 1 or x minus 1, because this function is periodic, it's still the same value. So this is well defined, and it will establish a homeomorphism between these two. And then you can see that going like this, it's the same thing as going like that, because that's the exponential map that we had before. This is the equivalence class map, and this is the map that takes this equivalence class and it sends it over here. And it's important to realize that this F is well defined, because it does not matter what you pick as your representative. So this example is not anything new. Let's look at another example. So in this example, so our topological space would be the real plane. So this is the real plane. And G, this is going to be the group generated by, let's call it tau. Let's call it tau h for horizontal and tau v for vertical. So what are these two maps? So tau h of a point sends that point horizontally. It translates it horizontally. This is integer translations. And tau v of x comma y, it's a vertical translation. So these are integer translations. Now, of course, if you do tau h composed with tau h applied to x, xy, you would just get a translation x plus 2 comma y, and so on, right? If you have tau h composed with tau v at x comma y, that would be x plus 1, y plus 1, and so on. And you should note that tau h composed with tau v is the same thing as tau v composed with tau h. So G, so we write that G is the group that's generated by these two automorphisms, right? That's the way you write it, that you have two automorphisms and you generate the group. So this just means you consider all possible ways of multiplying these together and their inverses. And as a group, this is of course isomorphic to two copies of the integers, because you can see this one, tau h, it behaves like an integer and they commute. So it's a commutative group, and as a group, it's isomorphic to two copies of the integers. And one can check, which I'm not going to do, it's not really that interesting. One can check G acts evenly on x. So x is the real plane. So let us try to understand the quotient. So can we describe the quotient x mod g as something more familiar? Now, this cannot always be done, by the way. Sometimes the quotient is complicated and it is what it is. But sometimes the quotient can be simplified down to a topological space that you're actually familiar with. In this case, it can be done. And it's similar to the previous example, because if this is your plane and you pick, let's say, the origin, then all translates, horizontal and vertical translates, they're equivalent to each other. So this lattice of points, they're all equivalent. They're in the same equivalence class, and so on. Now, if you pick a point inside this lattice, let's say right over here, by translating the point over, you can see that this would be the equivalence class of that point, and so on. So therefore, you only have to confine yourself to this square. Because if you go outside the square, it's redundant and everything is being repeated. You have a unique representative within the square, almost, not quite, but almost. So you have this square and you have a unique representative. The corners get identified. If you have a point on the edge, on the left edge, because of the vertical translation, it has to be glued with the point on the opposite edge. And if you have a point on the lower edge, it has to be glued with the point above it. So you have to take a square and you have to glue the edges together. So if you glue these edges together, I'm sure you've seen this before, you get a cylinder. So these are the vertical edges. And if you glue the horizontal edges, the two top pieces together, you put it together and then you end up getting a torus. So this is an interesting way of describing a torus. I know that previously we said that another way you can describe a torus as a product of two circles. This is yet another way you can describe a torus. So of course, this topological space is not something you can necessarily visualize because it does not consist of Euclidean points. It's more complicated than that. It's a collection of equivalence classes. But the point is, it is homeomorphic to something that you can visualize in a very nice way. So that's what this example is. So we have, so thus we've constructed, so we have constructed a covering from the plane down to the torus. And actually, this is the example from before. You can check. This is the same example from before. So in the other example with the torus, we were thinking of a torus differently as a product of two circles, and we had two pairs of exponential maps. But it really is the same example that we had before. So it might look different, it's just different language, but in the end, it's really the same example. Now, let me show you another one. Okay, so here, let's say G, not G, let's say X. X is the punctured complex plane. And G, this is going to be the group generated by rho, where rho, so this is an automorphism, is a rotation by 120 degrees. So rho of a complex number Z will map that complex number to itself, and you multiply by e to the 2 pi I over 3. So this is a rotation by 120 degrees. This is actually the reason why you want to stay away from the origin, because otherwise it's not a homeomorphism. The origin will go to itself under a rotation. But that's basically what this map is doing. So if you have a point, if this is Z, rho of Z would be right over here. That would be rho of Z. That would be 120 degrees. And then you can apply rho to this again. If you apply rho again, you would end up over here. This would be rho of Z. That's doing it twice. And if you do it 3 times, you will, of course, return back to where you were. So G, as a group, consists of the identity, it consists of rho, and it consists of rho squared. So that would be your automorphism group. So this is actually a group that contains only 3 automorphisms. And as a group, G is isomorphic to the integers mod 3. So let's describe the covering that we get. So the question is, can we describe X mod G as a more familiar space? So again, you cannot always do it, but sometimes you can. Can we describe this as a more familiar space? And here the answer is yes. In this example, you have to realize that this, you draw this entire line, and then you draw the line that goes 120 degrees, like this. And you realize that if you have a point, and then maybe you can also draw this one like this. And then you realize that if you have a point somewhere in this region, then moving it 120 degrees over would be the same point over and over again. So all of these are the same. So this piece and this piece are redundant. These two are redundant. So you really have to just confine yourself to this region. This is sort of the region where you have a unique representative. But then when you draw this, when you draw that region, you realize that if you have a point over here, it will be glued with a point over there, right? So the edges have to be glued together. So when you take the edges and you glue them together, perhaps you see what you're getting. You're getting a cone. You're getting a cone with the missing origin, so you get a cone. But topologically, a cone can be flattened. So you can just push it down. You can flatten it down. So if you flatten the cone, and you get the punctured plane again. So this is just the punctured plane. So the covering x to x mod g can be actually described something we've seen before, that x, this is the punctured plane, and this is homeomorphic to the punctured plane, right? This is homeomorphic to the punctured plane. And this quotient map would then be in this notation, in the notation of punctured planes. This would just be the mapping that was z cubed. That's a covering of the punctured plane. It sort of repeats twice because you have 3 fibers for every point, just like this one. That's just a mapping z cubed. So again, it just looks like it's something new, but it's not necessarily a new example. But let's give us a new example. So this is going to be a new example. So in this example, we're going to let x be the plane, and we're going to let alpha and beta be automorphisms of x, be described as, so alpha, so we have to say what alpha does to a point in the plane. And this is, we're just going to make this up. This is going to be x plus 1, comma y. And beta of x comma y is going to be negative x, y plus 1. And then g, this is going to be the group that's generated by alpha and beta. Now here you have to be a little bit careful. This is not going to be isomorphic to 2 copies of the integers. If you write this out, you will have the identity. You will have, I should have used set notation. So you will have the identity, you will have alpha, you will have beta, you will have alpha squared, beta squared, you have alpha beta, you have beta alpha. And here you have to be careful because beta alpha is actually different. Then you have alpha inverse, beta inverse, and so on. So it's all different automorphisms that you can get by repeatedly using alpha and beta together. So just to show you that they're actually not commutative, if you do alpha of beta applied to xy, you get alpha of negative xy plus 1. And if you apply the alpha map, you get negative x plus 1, y plus 1. And if you do beta of alpha of x, then you get beta of, so alpha xy, that's x plus 1 comma y. And beta of that would be negative x negative 1, y plus 1. So as you can see, you are getting, they're not commutative. But you can still write this group out. So this is going to be a more interesting example. And let's try to ask this question. So the question we want to ask is this. What is the quotient space? What is x mod g? Well, on a simple level, the quotient space would just be the set of equivalence classes that you get, of course. But what we really want is we want to be able to perhaps visualize this in some way, or maybe describe it as something that's familiar. And this is a more bizarre type of topological space that you may or may have not seen before. You probably have seen it before, but you probably maybe just seen pictures of it, but you've never seen it used in an example. And this is going to be an instance of where it appears in an example. So just like with the other examples, let's draw our lattice. So if this is 0, 0, 0, 0, if you apply alpha to that, it will get moved over. So it would be 1 comma 0. So these get identified in the quotient. If you take 0, 0 and you apply beta to that, you get negative 0, 0 plus 1. You go up here. So this is 0 comma 1. And if you apply alpha to this one, you get 0 plus 1 comma 1. So you get this one. So 1 comma 1. So all four of these get identified together. So these 4 points, they get they're in the same equivalence class. And you can actually check that the other lattice points also get identified. So just like the example with the torus, that all of these end up in the same equivalence class just like before. And just like we said previously, that you only have to really focus at what happens on this square. Because if you have a point outside the square, it's going to be equivalent to something inside the square. And so every equivalence class can be represented by a point somewhere in the square. So we have to therefore sort of analyze what happens on the square. So I'm going to get rid of these points. They're just going to confuse the picture. Now, this one's a bit different. Let's say, let me do it like this. So all of these get identified together. Now, let's say I pick a point on the left edge, right over there. So if you pick a point on the left edge, that point would then be equivalent to x plus 1 comma y. So it will be equivalent to the point on the right edge. Now, something interesting, it feels like the torus example all over again, but it's going to be fundamentally different when you see what happens horizontally. If you pick a point over here horizontally, actually, let me do it down here. Let me pick the one down here. Let's say you pick the point right over there. This point. Where is this one being identified with? So to get the other one, you do y plus 1. So you go up by 1. So you go here, and you do negative x. So negative x will actually put you there. So it's being identified with that point. So it's outside the square. But you can bring it back into the square by using this mapping. This one is then equivalent to x plus 1 comma y. So you bring it back. So it'll actually end up right over there when you bring it back, because it has to be moved by plus 1. And so you actually get to see something interesting, that on this square, the points that are on the vertical edges get identified across, and the points on the horizontal edges get identified sort of like this. So maybe if that's not clear, let me draw this one gets identified with that one. This one will get identified with that one. That one gets identified with this one. So this is like a more bizarre type of topological space. But let's try to visualize what we're doing here. Is if you take the ones that are going vertically and you glue them, you get a cylinder. Now this is how it's fundamentally different from the torus. On the torus, this point gets glued with that point. So you can therefore take this one and bend it over. But here it's actually the other way around. That point has to be identified with that one. So if you try to turn it into like into a torus, you're going to have a problem. So instead what you need to do is, you deform it a little bit. And you want to make sure that this point is being identified. I'm sorry, it's being identified with this one. So if you just bring these two together, you get the torus. So here you have to do it a little bit differently. You would have to take this piece. So let's see, what would be the? You would have to. So you see this opening over here, and you would have to make it pass through itself, and then put them together, and you get this object called a Klein bottle. And the Klein bottle is not something you can really visualize this. This is the way you draw it, but it is cheating a little bit because you're making it pass through itself. It's self-intersecting itself. By self-intersecting itself, it's not a one-to-one mapping, but that's the best you can do. So the Klein bottle is a type of topological space that cannot be embedded in three-dimensional space. It can be embedded in higher dimensional spaces, but it cannot be embedded in three-dimensional space, which means you cannot actually visualize it. So it's like a more bizarre type of example. So we just produced an example. So this shows that R2 is a covering of the Klein bottle. So this is a more interesting example. And let's finish with one more example. So let's say that X is S2. So this is the two-dimensional sphere. Two-dimensional sphere. And G would consist of, so as a set, it consists of the identity automorphism and alpha, where alpha is the antipodal map. So alpha of a point, X, sends it to negative X. So G is just isomorphic to the group Z mod 2. But there's only two automorphisms. And so this is X, and we're saying that if you have a point on X, let's say lowercase x, alpha of X, that's the antipodal point, that's negative X. This is alpha of X. And these two are being identified together. So yeah, so X and negative X being identified together. So let's describe what is X mod G. Of course, when we say what is X mod G, we're not saying what's the definition of the quotient. We're rather asking what is it as something that's more familiar to us. So perhaps you've seen this example before, but the idea here is that when you have your sphere, you have the upper cap and you have the lower cap. And every point in the upper cap is identified with a point in the lower cap. So the point in the lower cap are redundant. So you only have to really focus on the upper cap only. So this is the upper cap. And then if you have a point up here, then it's unique. It has no matching point in the upper cap. However, if you're located on the equator, then the point that it's identified with is on the on the opposite side of the equator. So to help visualize what's going on, just take this cap and flatten it down. So if you flatten it down, you get a disk. And you have a point here, and it's being identified with the point there. So points that are opposite each other across the diameter get identified together. So this point is glued with that one is glued with that one. And maybe you can see what happens. So you have your disk like this. If the points were glued across, if you were gluing them across, then you would take this upper piece, lower piece, you glue them together, and then you can see what you get. You would just get the sphere again, right? You would just get the sphere. This would just be the sphere again. But in this example, it's a bit more confusing because you're not just taking this portion and that portion, lifting them up and gluing them together. Before you glue them together, it's just like with the Klein bottle, you have to do a twist before you glue it. So imagine that you take this, you twist it, and then you glue it. And it's something I'm not able to draw, but what you get is called the cross cap, or sometimes it's called the projective plane. So it's denoted as P2. This is the two-dimensional projective plane. You can have the three-dimensional projective plane. It's really the same exact example, but instead of S2, you use S3. It's something it's even harder to visualize because you cannot visualize the three-dimensional sphere anymore. So this one is just like the Klein bottle. It cannot be embedded in three-dimensional space. So it's not something you can really draw. When people draw the cross cap, you have to draw it in a way that it self-intersects itself. So you're sort of cheating a little bit, but that's the best you can do. It's not really a type of topological space that can be embedded in R3. So this is just another example. And so what this example shows is, that S2 is a two-sheeted covering of the projective plane. So that would be enough for us today. So we'll finish here.